Hello, everyone. Why do we need math? The reason is life throws us lots of challenges, and these challenges need to be understood so that we could control them and live happily and prosperously. The quantities around us continuously change, and we need to control these changes by keeping track of them. So how do we keep track of quantities and thus changes? Well, by using functions in measuring them. So what's a function? A mathematical tool to keep track of changes. More precisely, a function is an assignment for every input. It assigns exactly one output. So there are like three pictures for examples. The first two are examples of not functions, and the last one is going to be a function. In the first one, we have two sets, A and B. In the set A, we have the elements 1, 2, 3, which are going to be potential inputs. And in the set P, there are two elements, A and B, which might be outputs. But in this assignment here, only 1 and 2 are assigned to A. So 1 and 2 are inputs, but 3 is not an input in the set A. So this is violating the situation that for every input, there must be an assignment. So for 3, there is no assignment. Because of this reason, this is not a function here. In the second example, for all of the elements in the set A, 1, 2, 3, there are some assignments, like 1 is assigned to A, 3 is assigned to B, but however, 2 is assigned to both to A and to B. But this is again violating our definition for the function, which means every input must be assigned exactly to one output. So this is violating that second part of the definition of a function. So this is not a function either. Now, the third example, we have again the same sets A, 1, 2, 3 with elements 1, 2, 3, and the set B with elements A and B. When you look at this, 1 is assigned to A, 2 is assigned to A, 3 is assigned to B. So all of the inputs are assigned. That's good. And then all of the inputs are assigned only one time. So that's the second part of being a function. So this is a function here. And then there is a terminology here. We actually give a name to the set of all inputs, the name domain. This set, the set of all inputs is called the domain of the function. And the set of all outputs of a function is called the range of the function. So here, A is the domain, B is the range. But there might be situations like this one in this fourth example. The source set, we must have all of the elements assigned to some element in the set B. But in the set B, not all of the elements might be some output. For instance, like 1, 2, 3 are assigned to A and B, but C is not coming from any input. It's not assigned to any input by this function. So we have to be careful talking about ranges. In this case, the range of the function is A and B. Well, the domain is naturally all of the inputs 1, 2, 3. So it's the whole set A, but the range of the function is only A and B. But remember, the set B is A, B, and C, which C is not in the range of the function. So we have to be careful. The range of the function can be sometimes, and usually actually generally, might be smaller than the whole target set B, okay? And then there's also in most of the books and also in our textbook, you might see these terminologies for the inputs and outputs. Inputs are also called independent variables, and outputs are also called dependent variables. So there's a way of visualizing functions via graphs. So what's a graph? The graph of a function f is the set of ordered pairs where the first point in the ordered pair is the domain, the input, and f of x, the second element, is the output here. Now, when we sketch the graph of a function, we usually use a horizontal axis, which is going to be used for the domains, Also, it's called domain axis. And then we also have a vertical axis, which is called the range axis, where the range is mapped to. So the function f of x, it has this blue graph here in this picture. And as you see, it is starting to take the first input from A. A is the smallest input here that f takes, and then it goes on with all of the other numbers in between A and B is the biggest input f takes. And then from this picture, you can see that A is mapped to C, B is mapped to D. So for any other point in between A and B, let's say M, it's an input, it is mapped to N. So how do we do this? We take this input, we go vertically until we hit the graph of the function. And then when we hit the function, we go horizontally towards the range axis to find out where this input goes to, giving us the output that it corresponds to. So input M corresponds to this output N, or actually I should say the output N corresponds to the input M. And this is how we read the graphs. And also by the graphs, we can easily figure out the domains and the ranges of the functions. So if you project the graph of the function f onto the domain axis, wherever it covers gives you the domain of the function. In this case, AB, closed interval. So we have a notation here, closed bracket, which means the point A and B are also included, and it also means that it's all the numbers between A and B. So x between A and B, here as you see, x can be bigger than or equal to A, x can be smaller than or equal to B. And for the range, if you project the graph of the function onto the range axis, then it will automatically give you the range. So in this picture here, it projects onto the closed interval C to D, where we use the notation here, bracket notation C to D. Well, this notation means that all of the numbers, Y values between C and D, and as you see, C can be also one of the outputs, and D can also be one of the outputs. So this is how we show that. Another example is, let's say we have a function given by some graph like this. The graph of the function is given by blue here. So there are these questions. First, A, find the values of f of 0, f of 5, and f of 6, let's say. How do we find f of 0? Well, we first find 0 on the domain axis here, and then we go vertically until we hit the graph of the function f. It hits here, then we project onto the range axis, but it's already on the range axis and it's equal to 2. So that means that f of 0 is 2. Then if we want to find f of 5, then first we find 5 on the domain axis, the horizontal x-axis. Then we hit the graph of the function, but it's already hitting the graph there. Then we project onto the vertical axis, y-axis, to find out the output. Well, it corresponds to 0. So that means f of 5 is 0. And for f of 6, we first find 6 on the horizontal domain axis. Then we go vertically until we hit the graph. Well, it hits the graph here. Then we go project it horizontally, and we come to hit -1. That means f of 6 is equal to -1. Now, the B part of the question asks, find the domain and the range of the function. Okay, so if we project this blue graph onto the domain axis, well, it covers every number from 0 to 6. Like it covers everything from 0 to 6. So that means the domain of the function is the closed interval 0 to 6. And the range of the function is, we project the graph onto the range axis. Well, it projects down to -1 to 3. So that's the range, which is -1 to 3 closed interval. So another example is, let's say, sketch the graph and find the domain and the range of each of these functions here. In A, we have f of x, which is given by 2x plus 1. So if you want to sketch the graph of a function like that, we can always take couple of points, x values, let's say here -1, 0, and 1, and then we can plug them into the function. So -1 will become 2 times -1 plus 1, that's -2 plus 1, then that's equal to -1. If we plug 0, then we are going to get 2 times 0 plus 1, that's equal to +1. And if you plug 1, 2 times 1 plus 1, that's equal to 3. So these points are here. This is -1, -1. This is 0 plus 1. And this third point is 1, 3. So that's a line actually. Now, whenever we have a formula like this, some number times x plus some just another second number, this is actually a linear function formula. The reason we call it linear is when you sketch the function, you have a line graph, just like this one. And then for a linear function and for all lines, we have two information which describes the line uniquely. One of them is the slope, which is the coefficient of x, that's 2 here. And the other data is +1. This +1 is called the y-intercept. The reason is if you plug 0 for x, like this second point, if you plug 0 for x, you get +1. So that means that this line intersects the y-axis at +1. So that's why it's called y-intercept. It has an intersection with y-axis there at +1. The second information is the coefficient of x, which is called the slope. So that means that if you go 1 unit towards right in the horizontal direction, then in the vertical direction, you will increase by +2. Okay, so that's the slope, 2/1. And that's the second information about any line. In this case, that's equal to 2. So this is the graph of the function. Now, for the domain and the range of this line, if you think about it, we can input any real number into this 2x plus 1 function for any line, for most of the lines. This is the case, except for the horizontal lines and the vertical lines. They are special cases. We will see them also later. But for a general line, when the line is not horizontal or vertical, just like a line like this, then you can input any number. You can input 0, you can input 1,000, 1 million, or you can input -1,000, -1 billion, and you can keep doing this. So that means the domain, the set of all inputs, is all real numbers, which we can show by this notation, -infinity to +infinity, or with this notation. Most of the books show it this way, capital R, which is shown in this way. So that's the domain of the function. And by the way, I want to say one more thing here. When you see this -infinity to +infinity, these are not real numbers. -infinity or +infinity are not real numbers. But -infinity is a notation, which means that you can go negatively as large as you can. And that's still fine. Or when you see +infinity, that notation means that you can choose any positively large number as you can. So that's a notation, which means that all positive numbers, as large as possible, is in the set here. So -infinity, +infinity means that. What about the range? Well, if you project the graph to the vertical axis, that's one way to see. But since we have a finite picture here, we cannot have an infinite, -infinity to +infinity domain axis. Now we have to make some reasoning here. Since we can input any number, you can also get output of any real number as well for a line function like this. Then the range is also the set of all real numbers in the same way. We can show it these two ways too, -infinity to +infinity with the parenthesis notations, which also can be shown shortly with the capital letter R, okay? The second function was g of x equals x squared. So that means x times x, 2 times. So we can pick bunch of points, let's say -2. So then -2 squared is -2 times -2, which is +4. We can pick -1. -1 squared is -1 times -1, which is +1. 0 squared is equal to 0 times 0, which is 0. 1 squared is equal to 1 times 1, that's equal to 1. And then 2 squared is equal to 2 times 2, that's equal to 4. So we can just plot these points here. So -2 and +2 goes to 4, -1 and +1 goes to 1, 0 goes to 0. We have a parabola picture like that. As you see, it's a symmetric graph with respect to the y-axis. Now, the second part of the question is the domain and the range of this function. Well, domain is what? If we project this graph onto the domain axis, we will get the domain. So look at the projection. Now, we can plug any negative number, any positive number, and that's going to give us some positive number. Taking the square of a number will give us a positive number. If we plug 0, that's the exception. We will get 0, which is not positive or negative. But it gives out positive numbers, and you can take any number you like. You can take 1 million. It's going to give you some bigger number. You can take 1 billion. It will give some bigger number, or you can take negative, the bigger numbers. So the domain is all possible real numbers, which means real with the notation r, or -infinity to +infinity. For the range, obviously, when you project the graph onto the range axis, it's going to cover up all of the positive numbers starting from 0. So it's all positive numbers and 0, or you can also say all non-negative numbers, which is another notation used in the books. So you should be also used to this kind of notation. Okay, so another example is this function. If f is 2x squared minus 3x plus 1, then also let's say h is some non-zero number. It can be anything. It can be 1, 5, or -4, -7, whatever. It can be any number except for 0. But it's an abstract number, h. And we want to evaluate f of a plus h minus f of a divided by this number h. Okay, here a is an abstract number. It can be, again, anything. H is another abstract number, only non-zero. So what do? We just first remember that a plus h is an input, and we will plug it to the function, which gives us this first expression written in blue, 2 times a plus h squared minus 3 times a plus h plus 1 all over h. And then if we input a into the function, we are going to get 2a squared minus 3a plus 1 divided by h. So now, what is a plus h squared? It's a plus h times a plus h. So a times a is a squared, a times h is h times a is ha, and h times h is h squared. So we get 4 terms. But if you look at a times h plus h times a, they are same actually. Why? The reason is you can switch the order in multiplication, like because you can have 2 times 7, or 2 times 7 is 14, which is also 7 times 2. Or you can think like 3 times 4, which is 12. That's also equal to 4 times 3. So you can always switch the order in multiplication. That means a plus a times h and h times a are same. So we just write 2 times h ah. You could also have written 2 times ha, but pick one of them, 2 times ah. And then multiply it by 2, you will get 2a squared plus 4ah plus 2h squared. And then minus 3 times a plus h will give minus 3a minus 3h plus 1. And minus of the f of a will mean that we will have to distribute the minus to all of the terms inside the parentheses. So minus 2a squared plus 3a minus 1. Now, when we look at this long expression here, there are a bunch of cancellations here, by the way. So if you look at it, there are cancellations like this term. Okay, now I'm going to pick a different color here. So this guy cancels with this guy. And then 3a and minus 3a cancels. So they cancel. Okay. And plus 1 and minus 1 also cancel out. Well, then what have we remained? What have remained? Well, 4ah plus 2h squared minus 3ah. 3h remained. So, and we also have a division by h. Now, if you look at the terms here, like we have h, a common term, 2h squared means 2h times h, that's another common term, minus 3h, 8 is another common term. So we factor h from them, then 4a will remain from the first term, plus 2h will remain from the second term, and minus 3 will remain from the third term. Then you can divide h by h. It's going to simplify to 1 over 1, which is 1. So all that remains as the final answer is 4a plus 2h minus 3. Now, this computation may seem like out of the blue. You might think, why did we just care about this? The reason is, you will see when we start talking about derivatives, at first we will be doing computations just like this. So that's a computation we will do later again. Anyway, last part is, we can represent functions most commonly in 4 ways. There are like verbal representations, which is like by some description of words. Okay, so the function can be described by just, by a sentence or by some set of words, or it can be represented numerically, which means if the function can be given by a table of values, then it's a numerical representation, or it can be given by a graph, which is a visual representation, or it can be given by an explicit formula, just like these functions we have worked, like x squared is an algebraic explicit formula, so it's an algebraic representation, or 2x plus 1 is a formula, f of x equals 2x plus 1 is a formula, so it's an algebraic representation. Some example, just like that x squared, if we say x squared, then that's the algebraic representation. The graph is the visual representation here. And the table, which we have formed earlier, that's the numerical representation. Or you can say all outputs are squares of real numbers. That's a verbal representation. So in the real life, guys, we take a real world problem, formulate it into a mathematical model. Well, we take quantities in the real world problems. So in this real world setting, we have quantities. Okay, let me just pick a different color, I guess. Yeah, so in the real world, we have quantities. We want to observe and work on their changes to understand situations. So in the mathematical models, quantities correspond to functions, okay? So we formulate them into mathematical models, quantities become functions, and then we play with this mathematical model, solve the mathematical problem, playing with the functions, of course. We get a mathematical conclusion or a solution, and we interpret it back into the real world, and we get some predictions. So we will decide, okay, maybe I should do this, or maybe I should do it this way, or maybe I shouldn't do it. So that's how we use functions in this context. Okay, well, this is the end of this video.